if it meets the surface of a new medium, the thing it's traveling in, if it encounters a new medium, I have surface in my notes, but I like boundary better. That is different or varying in space or time. That's kind of our rule. And so our ray approximation is meant to make our lives easier. So rays of a given wave are straight lines. Perpendicular to the wavefront. Eek. It's the thought that counts. So So rather than trying to draw the wave fronts, we're just going to represent the things perpendicular to the wave fronts as rays. And it'll describe the travel of the wave. Is that kind of maybe sort of all right?
Wait. Right now, I only see the lines. So what does ray mean?
So the ray are these black lines.
Oh, okay.
And they're really just meant to carry information about the direction of travel and of the orientation of the wavefront.
Oh, okay.
And so really, we're going to stop drawing the wave fronts and just represent them by rays.
Oh, okay. So that's why we need that needle hole to go through, then we can see the wave. Because on that whiteboard, I see waves, but in here, I only see the lines.
So I want you to think of these as our wave fronts, right?
Oh, okay.
But it's too complicated to keep drawing those.
Mm-hmm.
And so instead what we're going to draw is we're going to draw the thing that's perpendicular to them,
Oh, okay.
which are the rays.
Mm-hmm.
And they're really just a visual tool for us.
Oh, okay.
Yay? So do it this way. So sadly, I think I've said words to this effect previously, but physicists could probably use a PR firm. We're not the best at naming things. I don't think that it's purely just an effort at job security, like making it harder to learn it intentionally. But for better or worse, that's kind of where we land. We are going to spend a fair bit of time over the next few weeks talking about reflection, refraction, and diffraction. And those all have names that, at least to my ear, sound similar enough that it's frustrating, right?
Reflection, reflection, and diffraction.
Reflection, refraction, and diffraction.
Oh, okay.
There's some stuff I don't remember learning anymore. That's the danger, right? It's that if you don't remember learning it, it's harder to remember that it doesn't come naturally. But one of the things I do remember from when I was still a younger person trying to learn this is that it seems stupid to me that those three things had such similar sounding names. But especially with the masks, if you have any difficulty telling what I'm trying to say, reflection, refraction, or diffraction, ask and I'll try to make it a little more clear. But this first one that I wanted to kind of describe is ode to diffraction. And what I will tell you is particles don't diffract. Waves diffract. And so the fact that you see this for light, again, should make us feel confident that we're using a model that will work, right? That we're treating this as waves, because it is, right? Well, so this will be one of the last times I actually try to draw wave fronts, because it's too much effort. Okay, so oh goodness. See, this is why I don't do this.
Hardworking.
Okay. I'm going to call that well enough. And then probably way more rays than I really need to draw. But my OCD now wants me to finish doing what I was doing. Yay? So if the obstacle is, this slit, it's kind of big compared to the wavelength, you don't see much diffraction. But if instead the obstacle and the wavelength are in the same ballpark, then we're going to start to see some significant diffraction. trying to preserve the space between wavefronts. And I didn't fail entirely. See something start to develop some curving. If the slit starts to be on the same size, even smaller, that's where you get kind of this type of behavior. So the fact that you can see this type of behavior for light implies that light has the properties of waves. It's just that in a few weeks I'm also going to show you that some experiments light displays particle properties also. Kind of depends on how you ask the question. So here, lambda is small compared to, how do I want to write this? Over here. When you can make a fair comparison between the wavelength and the slit spacing, you start to see noticeable diffraction. You can even see this. I tried this with these lights. If you put your thumb and forefinger near one another and look at a light source, you'll see a weird fringing pattern in the space between your thumb and forefinger right before your thumb and forefinger touch. Depending on sizing your fingers, you might even be able to see that between kind of the gaps in your fingers as you push them closer together. Okay, so let's, oh goodness. Is it okay if I cover the left panel?
Sure.
Thank you. Maxwell was one of Einstein's heroes, by the way. So diffraction, let's look at reflection. This is the one that I'm guessing you're already pretty well versed in. So coming back to our model again, rays of light travel in straight lines unless they encounter the boundary of some new medium, right? And so here, light is traveling in air or maybe a vacuum, and then there's some mirrored glass here. It encounters the boundary between those two different media, and that can cause it to alter from its straight line path. And so I want to focus on two rays that come in parallel. So if the two rays come in parallel, they also reflect parallel from a smooth specular mirror. So if instead, so we call this specular reflection. When I go to the doctor and they stick that like little microscope thing in my ear or nose, what's that thing called? Stethoscope goes speculum?
Let's go with it.
Uh,
It has the light on it.
They're like tube on a stick.
Sure.
Small flash.
Speculum has a lot in common with specular. If you're going to stick that thing in my ear, what must be true of it? A couple things. Well, yeah, it has to be clean. It was me we're talking about. What else? That thing better be smooth, right? You're not sticking some sandpapery thing in my ear. So when you think specular reflection, I want you to think off of a very smooth surface. We're going to define smooth in terms of the wavelength of the light, but specular reflection is reflection off of the smooth surface. So we've got some rough surface. I actually think that I get that.
So would this be the same concept as why you can see reflections off of like water bottles and soda bottles?
Sure. It's
Specular
also,
reflection.
any other lazy souls out there like me who make use of a microwave on regular occasion? Yeah? You don't have to admit it, I don't care. I wear my laziness proudly. You ever, or not to out the one poor person who agreed with me on this, but does anyone who used the microwave ever get impatient and like kind of look in through the window?
Yeah, me. I will look at it.
So,
I can see the water boiling.
Thinking some ramen, huh?
so the Maxwell tells us that light is an electromagnetic wave, right? So types of electromagnetic radiation. Radio, infrared, visible, ultraviolet, X-ray, gamma ray. Part of my research career involved CMB, cosmic microwave background, leftover radiation from
There's
the Big Bang.
X-ray there also.
What's this?
There's X-ray also.
Sure, these are types of electromagnetic radiation. So I'm going to add microwave to the list just because it's been very important in terms of understanding the universe.
Oh.
But it's also, you know, it's the visible colors: red, orange, yellow, green, blue, violet, right? Near and far infrared. If you wear sunscreen, you guys are young. There's still hope for you. Sunscreen, moisturizer. You don't want to look like this when you're. Believe it or not, I'm in my 20s. No, I'm not. 220s. But you just still, at any age, you don't want to look like this. Sunscreen and moisturizer. I actually think the masks are protecting your skin. It's a different kind of moisturizing, right? But X-rays, we often talk about hard and soft. But if you wear sunscreen, maybe you've read the thing UVA, UVB. Yeah.
UV
So
umbrella.
exactly. Microwave is just another kind of electromagnetic radiation, but it's in the right energy level that it can cause an excitation of water molecules. What's the goal of my microwave?
Make the food get hot.
Raise the temperature of my food. Yeah.
Oh, yeah.
And so I want to add to the internal energy. Specifically, temperature is a measure of average translational kinetic energy per particle in a given sample. I lied to you when I said you were done with thermo. You're going to wake up screaming that for years. Don't worry.
I know you're not.
So what happens with microwave, it's actually in a range where it can provide rotational kinetic energy to water molecules. You're hoping that as they're rotating, that they bump into their neighbors, and some of that rotational kinetic energy turns into translational kinetic energy and warms the food. Right? That's the goal.
I
So-
heard that if the water is under enough pressure, it could stay in its solid form, even if it's really hot.
You mean not boil?
Yeah, well, it can just stay ice.
Stay liquid? Oh,
You said it
there
creates
are
a
all
stream.
sorts of games. So
Does it plan it like that?
so you're talking about phase diagram stuff.
Yeah.
So yes, that's absolutely true. You can adjust you can play fun games with phase diagrams. But I thought you were talking about there's kind of maybe an overblown concern. I'm an old man. I've never seen this happen in person. That if you heat water in a microwave, sometimes those collisions don't happen and you put a lot of energy into the water, but it just hasn't started boiling yet. And as soon as you move the cup, it'll jostle it enough that that energy turns to translational, and then it'll rapidly go past boiling and splash. I think that probably can happen. I think it probably
I
doesn't.
have did that. Like I
happen
put
very often.
half of the coffee there, and then I forgot. All the coffee is burned
Oh, did it?
everywhere. Oh,
Um, all of this fun. I would love to talk about microwaves with you guys more. But if you ever look into the microwave while it's on, right? Well, again, I point this out because I don't know a lot about biology, right? I have a Milky Way candy bar for breakfast every day. That tells you what I know about biology and stuff like that. But someone told me once, and I believed him, that there's a lot of water in a mark, right? That my cells have some water in them.
68% of you.
I'll believe you if you know, unless you tell me that Milky Ways are bad for me. I'll believe you. It's the one thing I refuse to accept. But if I'm a lot of water, wouldn't it not be such a great idea to expose myself to microwave radiation?
No,
I don't want to cook myself. I'm very certain I don't taste good. So, in one of those doomsday scenarios, I should be the last person that gets eaten. Pretty sure it wouldn't be
Too
enjoyable.
much bone.
you could run fast.
So, So visible light can clearly come out of the microwave. I can see my bean and cheese microwave burrito about to explode, right? I like that hot enough that there's no way any germs are surviving. Right? But I'm hoping that the good people who made my my generic knockoff of a real microwave have come up with some way of making sure I'm not being exposed to microwave as I press my nose against the glass. What's going on? What does the glass of a microwave oven look like?
Double panel. Double panel.
That's like a few layers.
So it does have multiple layers. One of those layers is a metal mesh.
Yeah, that's the first layer.
So obviously I can't draw. You can see how much money I spent on my microwave. That's what the window looks like. This listing, anyone tell me what this order is as I go down?
What the order you want to say? You want to say UV?
Wait,
Right now?
the-
Or you want
And
to
So-
so why do you mean like which one is the strongest one?
Okay, nice.
So frequency is increasing as I go down the list. Wavelength is increasing as I go up the list. Okay?
Yeah.
Remember from your physics 130 days that the wave speed goes as f times lambda. In this case, the constant speed of light c goes as f times lambda. So as the frequency increases, the wavelength has to, as the frequency increases, the wavelength has to decrease. Yeah? Does that make sense?
Yes.
So compare the wavelength of microwave EM radiation to the wavelength of visible light.
It's gonna be a lot longer.
Wavelength of microwave radiation is significantly larger than the wavelength of visible. In fact, the wavelength of microwave radiation tends to be on the order of a few centimeters, give or take. The wavelength of visible light is on the order of
Nanometer.
hundreds of nanometers, right? Yay? So to that end, the visible light passes straight through these giant holes, right? But what does the microwave see when it gets to that panel on the wall? It sees a mirror.
Oh, mirror.
So the microwave can't get out. I haven't been cooked yet. But the visible can pass straight through, right? So when I was telling you specular, that's going to depend on what specifically we're talking about. I mean this way, right? We're going to look at the wavelength. So that note that now two rays that come in parallel don't necessarily reflect parallel, right?
Yeah.
We call this diffuse reflection. So specular reflection means that if rays came in parallel, they reflect parallel. Diffuse reflection means if they come in parallel, they don't necessarily reflect parallel. Sir?
What would the reflection be for like surface of water? Because it reflects visible light and allows it to pass through.
So some of it is transmitted, some of it is reflected. The reflected part is still largely specular. The transmitted part is actually refraction. And that's the thing that clearly I don't get to today, but we'll get to on Wednesday. So there, if you've ever put a straw into a glass of water and it looks like it's bent at the surface, that's refraction. If you've ever stood in a shallow pool and your legs seem short, that's also owed to refraction. So
That's the light. If you're underwater.
that's the light. So there's kind of two options when light is in one medium and encounters the boundary of the next. It can either reflect, bounce back at the boundary, or it can pass through. If it passes through, it refracts. If it bounces back, it reflects. In truth, in many cases, it does both. Some of it bounces back, some of it transmits. And so we'll explore that too. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you on Wednesday. Although tomorrow I'll do another problem session.
Question on that. Isn't it that the